Strange as it may seem, ice skaters do not skate on ice. Even the smoothest ice isn't slippery enough for that. Ice must be lubricated before anything will slide on it. The skates really glide over a thin film of water under the skate. Here's what really happens. The blade of the skate cuts a groove, and the pressure melts enough ice to cover the groove with water. The thin film of water between the skate and the ice acts as a lubricant on which the blade can slide easily. A lubricant is something that makes things slippery. Water is sometimes used for lubrication, especially where it can be supplied in large quantities. It takes a lot of water to keep this seagoing roller coaster from sticking to the chute. In some boats, a steady flow of water from the outside lubricates the shaft, which carries power from the engine to the propeller. However, water has disadvantages as a lubricant because it won't stay where it is needed. It pulls apart too easily, and it won't keep its film between moving surfaces. When the surfaces are squeezed together with enough pressure, the water is squeezed out. But there are better lubricants than water. When a sticking bureau drawer is stubborn and bulky, we can make it slippery with a little soap so that it will work easily. For the launching of a liner, tons of tallow or hard grease are used to make a smooth, slippery path. A simple experiment shows the effect of a lubricant. We use a block of metal polished to an even finish and a metal incline as smooth as glass. Without lubrication, the block will not slip. The two metal surfaces are in actual contact. However, if we lubricate the same surfaces, keep them apart with oil, the block will slide of its own weight. Here, magnified thousands of times, with the help of microphotography, we can see what happens when a metal surface glides over another surface of metal riding on a film of oil. Oil is a good lubricant because under high or low temperatures, it keeps an unbroken film to hold sliding surfaces apart, and it won't evaporate. Oil is liquid enough to get into small openings between closely fitting parts. Oil is thick enough to form a cushion that stays where it is needed, and it is elastic enough to make a film under pressure. A small flywheel bearing shows why it is necessary to use a good lubricant. We first remove all the grease or oil. When we spin the wheel, the metal surfaces rub against each other. Without oil, they grow hot. The soft bearing metal is melted. Friction binds the moving parts together, and soon the flywheel will stop. Without the protection of oil, both surfaces are ruined. There are three general ways of circulating a supply of lubricating oil to the parts of a machine. We can arrange a bath of oil so that moving parts can splash into it for lubrication. We can provide a supply of oil on a higher level so that it will trickle down through a system of tubing onto the moving parts. The force of gravity furnishes the power to carry a steady flow of lubricant where it is needed. If we want an extra amount of lubrication, we can force a stream under pressure directly onto the sliding surfaces. By controlling the pressure, we can control the lubrication for different speeds. There are many moving parts and many types of moving surfaces in the automobile engine. Consequently, the engines in our cars today use all three methods of lubrication to provide for the wide range of speeds and loads. The heart of the lubrication system is the oil pump. In the oil pump, the two revolving gears create a suction as the teeth move apart. This suction draws oil from the storage reservoir or oil pan. The gear teeth carry the oil around as they revolve, and then, as they mesh together, force it to the engine parts. Each gear tooth sends a strong spurt of oil, and at normal engine speeds, the result is a steady, smooth flow. In the modern engine, the main bearings carry the load of the crankshaft as it whirls at hundreds of revolutions each minute, and plenty of lubrication is needed. To get this lubrication, a constant stream of oil is pumped under pressure directly into the main bearings. The camshaft has the job of opening and closing the valves and needs an elastic cushion to protect it from friction. The oil flows through tubes to the bearings which carry the camshaft, and more oil flows out through a nozzle onto the timing gears which drive the camshaft. To keep the valves in smooth operation, oil is pumped up into the valve mechanism. A special method is used to lubricate the connecting rods. A high-pressure stream of oil is forced through nozzles in the base of the engine, and each jet of oil is accurately aimed to strike a scoop or dipper on the bottom of a connecting rod. The oil is forced up into the connecting rod bearing by the scoop-like action of the dipper as it strikes the jet. In scooping up water, a locomotive uses the same principle. A special motion picture camera equipped with what is called a stroboscope lets us see the action of the dipper on a crankshaft that is actually revolving at a speed of 3,600 times every minute. There is a hole in the bottom of the connecting rod through which the oil passes from the dipper into the bearing. At high engine speeds, the oil enters the dipper at the rate of 120 miles an hour. The barrel shape of the dipper picks up less oil at low speeds than at high speeds. And as the connecting rod splashes into the trough, it throws a spray of oil over the cylinder walls. This spray of oil forms a smooth film to lubricate the speeding piston as it slides up and down in the cylinder. A special ring on the piston controls the amount of this film. The excess oil is scraped off and carried through holes in the side of the piston to furnish the main lubrication for the piston pin. A steady stream of oil flows through the engine, bathing the crankshaft, the camshaft, valves, and pistons and connecting rods, covering all the moving parts with a protecting film. The modern engine uses the same oil over and over again, 4 times a minute at normal speed. In order to do this, it must be cleaned and cooled. Each time the oil passes through the engine, it is filtered so that dirt and impurities can be kept from the polished surfaces. The oil is cooled in the bottom of the engine and allowed to rest in the oil pan. Efficient crankcase ventilation removes hot, corrosive gases so they cannot contaminate the pure oil. A tremendous stream of cooling, cushioning lubricant is pumped through the engine. By connecting a hose to the pump and arranging a return pipe, we can see the amount of oil that flows from the pump each minute that the engine is in operation, enough to fill a bathtub in 3 minutes. Closely fitting, highly polished parts, moving at high speeds, year in and year out, demand an adequate supply of good, clean oil to protect them from friction and wear, to give power, economy, smooth, silent operation, and long life, with every part riding a film of oil.